And for the second one, the answer is yes, because these algebras are PI. I discuss this a little bit later. But there was a theorem. So for PI algebras, we have that the answer is yes in all the cases. For 1, 2, 1 prime, 2 prime. And the answer for new algebras was given by Levitsky using some structure theory. And for algebraic by Kaplansky. In both the cases it was in the late 40s, I think. Okay, Kaplansky was 1946, Levitsky was, and Kaplansky was 1950. So, too late 40s. So, also if you read the book by Herstein, you can see how you apply the structure theory to prove these results. This is something they start, first they prove this for fields, then they prove for division algebras, then they step by step extending more and more and more until they prove this in the general case. And now I want to say a couple of words about another approach. In the
You mean by for PI-Algebras? This last statement?
Okay, the last statement here for PI-Algebras is the following. If the algebra satisfies a polynomial identity, it's finitely generated. And every element is algebraic. It doesn't matter finite degree or the degree is the same or not the same for all the elements. Then the algebra is finite dimensional. If the algebra is finitely generated on PI and this is new, every element is new, then this algebra is nilpotent. Here you don't have one in the nilpotent case, of course, you have no one in the algebra, because otherwise it cannot be. So, Kirchhoff, he proved a theorem, so the theorem of Kirchhoff in the 50s, I think it's 1957, but maybe it's 1956, is the following theorem. So if the algebra R is generated by R1, Rd, and satisfies a polynomial identity of degree n, then there exists an H, which is a positive number, with the property that if we form, if U1, U2, etc., Un are all products, Ui, this is Ri1, Rik, and k is less than n, the degree of the polynomial identity, then R is spanned as a vector space by all products. You have Uj1, A1, Uj P, AP, where P is less than H. So, I repeat once again. You have an algebra which is generated by a finite number of elements. It satisfies a polynomial identity of degree n. You form all products of the generators of degree up to n minus 1.
Excuse me, I don't quite see that. There is what?
There is an element H which I put here. So
And then this odd element, the last
you take all the products of degree up to n minus 1. And there is some integer h with the following property, that the algebra R is spanned by, as a vector space, by monomials on these elements. But these monomials are something like monomials in h variables, as commuting in h variables. So for example, you can take R1, R2, R3, R1, R2, R3, etc. And maybe you can have here, maybe something, maybe you have, for example, if the algebra, you can have any product of elements of the generators. And here the indices can be any. Maybe you have no repetition, okay, you have repetition because they are finite number, but no periodicity, for example. This sequence can be very, very bad and very long. But nevertheless, the statement is that this element is a linear combination of words, some U, J1, A1, GI, P, A, P, where this P is bounded by H, cannot be too long. So this behaves like, so this is something like a monomial in commuting variables. Because you have here a finite number of elements, finite number of indices.
So this R is an algebra over a field.
Over a field, yes. So this is an algebra over a field. So R is an algebra over a field K. You know that this is finitely generated. So maybe I give you an example of this before to. I'm not going to prove the theorem because the proof is quite combinatorial and quite difficult. I want to give some consequences. But assume, for example, that you have, example, the algebra R satisfies the commutator of length 3 equals 0. Assume that this is an identity. So we have that n equals 3. Assume that R is generated by R1 and R2. We have two elements which generate the algebra. Then you form U1 to be R1, U2 to be R2, U3 to be R1 squared, U4 to be R1 R2, U5 to be R2 R1, U6 is R2 squared. Then there exists some H. There exists some H. Even this H can be, in this case, it can be chosen to be 3. Here, for this special case, H is 3. Such that R is spanned by such thing. You have U1 in power A, U2 in power B, and I write here also U4 in power C, and I write also U1A or U2 in power B, and I write U5 in power C. So this is a heavy exercise. This is not obvious. So this means that every element of the algebra, this is simply a linear combination of the following. You have R1 in A, R2 in B, and maybe you have here or R1A, R2B, and even you can have R1, R2, or R1 in power A, R2 in power B, R2, R1. Okay. I write here, okay, I write this one because it became. So this is the real case, what happens in this one. So the theorem of the theorem of Kirchhoff gives that there is some H such that you have products here maybe with some repetition, such that here you have, for example, here you have R1 in power A, R2 in power B, you have R1 again. You have some repetition, but you have here, this is like a monomial in 3 variables. The first variable is R1, the second variable is R2, and the third variable is R1 again. So this is this statement that are expanded by this element where A and B are non-negative. This is, you can consider this as a theorem because it's used a lot of facts about this polynomial identity. But if you want to, and of course the characteristic of the field is different from 2. You add this one. But in the general case, if you have any polynomial identity, you have something similar. Every element is a linear combination of monomials on some finite set of variables. U1, U2, U5, or maybe U1, U2, U1 again, or something. And each of these elements is a bounded degree with respect to the generators. So this is the Kirchhoff theorem. This theorem was discovered in the West quite late, because in that time the Russian literature was maybe not translated or translated not in the best possible way, or maybe translated much later. And I think that Jacobson gave a talk, and this talk appeared in a written form in some meeting. It was devoted to 3 big achievements of the Soviet mathematics, Soviet algebra. And one of them was the Kirchhoff theorem. The other, this is called the Kirchhoff height theorem because this H here is called the height of the algebra R. So this was the Kirchhoff height theorem. The other was the existence of central polynomials given by Razmisov, and I don't remember what was the third in the moment. But this theorem appeared in a weaker version in the talk by Jacobson, because when you present some theorem, you don't give this in full detail. This is the full detail. And okay, Daniel told me today that if there is a joke, it should be not a stupid joke, because otherwise it can't be. But record it. But this is a real story. Rowan wrote a book on ring theory, and he proved there included the theorem by Beryl that finitely generated PI-Algebras, they have a finite Gelfand-Kirov dimension, which means that from quantitative point of view they behave as polynomial algebras. And I saw in the book that this was written, that now we present the proof by Mitsur and Drensky. I was a little bit surprised because I met Mitsur only 3 times in my life and for a short time. And how we did the proof of the theorem. But I remember that it was in the early 80s, one of the International Congress of Mathematicians was in Warsaw. And in that time in Warsaw there was the regime of the General Jaruzelski, and it was a lot of countries, they boycotted the Congress. For example, the Americans who were there, they were as private persons, not as Americans. Not as an Americans, and Gromov was the first speaker, and Mitsur was the chairman, so they just presented us to each other, and Gromov was not in the hall, and Mitsur announced 1 hour break, because not to move the shadow of the conference, so let's go to the buffet fast to take a place to have. And he told me, you know, Beryl proved this theorem that finitely generated PI-Algebras are finite Gelfand-Kirov dimension. I already knew this because it appeared 2 years before, and I told me, you see, if he used a weaker version of the Kirchhoff theorem, but if you use the correct version, the stronger version, which is I wrote here, it should follow. I mean, so thought about 15 seconds, and of course it should follow. So after this, he told the proof to Rowe, and honestly wrote that this is our proof. But now I want to show you how the Kurush problem can be derived from here.